Hi everyone, today I'm going to talk about how to encode time in deep learning. So usually we have two options. The first one is to use continuous features, and the second one is to use categorical features. For categorical, it might work in simple cases when we use just days of the week, like Monday, Tuesday, Wednesday, etc. So we first assign the index for each of them, and then dense layer will learn the dense representation of each of the categories. So it will be just a list of numbers, .7, .5, etc. For cases like January 27, 2025, it's not gonna work because we'll have too many categories where we encode each of the date separately. And secondly, the data will be probably very sparse. So this embedding won't be able to learn which of the categories are close to each other. So our next category is January 28. And it will be unlikely that the learned dense embedding are going to be similar. So another approach is to use continuous feature, and we have all the distribution of all the data and times on this line. This is going to be like minimal, and this is a maximal, and all our events will land between this range. For real events, the difference between Monday and Sunday could be huge. So if the change is too little, the neural network won't be able to spot trends based on the week. And what about the time of the day? Data and time can affect what's happening based on the time of the day, or even less. It can be even minutes, sometimes seconds. So we need to have something smarter. And the best approach, the simplest approach, is to use something like continuous feature, but with ability to scale for larger ranges. For to encode data and time, we can use cycling encoding. And the idea, instead of having like a value distributed along line, we'll use a cycling function for that. So our time will be an angle on this line. And this is our starting point. And our time here is a point somewhere on this line. Now if we change time along the curve, we're just changing the angle. And instead of tracking the angle directly, we'll be tracking sine and cosine functions of this angle. So our dot here will be represented as a combination of sine t and cosine t. But what happens if we run out of space? So if we reach the zero coordinate and we start it over. So now we don't know what time point it was. So that's not a problem. We can create one more component that will have a lower frequency. So this is our first component, and that's going to be a second one. So once the time is changing, this component will change too, but with 1/2 of the frequency of this time. And we also track its sine and cosine values. And we can continue. So we have multiple components. And if we draw how the functions look like, this is our first component. Then we have cosine, it's the same frequency. Then we have the second component, and the frequency will be lower. So it will be changing slower. And the same cosine function. And the third one will change even slower, and so on. If we take any point on time, like this one, we have a set of values. This one, and etc. So those values will be our representation of the time at a certain point. So it's dot 7. There's gonna be -1. That one is, let's say, 0. It's gonna be 0.3, 0.2, and this one, I don't know, 0.1. And this is our dense vector. So this is our vector. We can write it down in a normal way. So 0, 7, -1, and etc. Yeah, so this is it, and it's a dense representation. We can use it. The number of frequencies we can choose is based on how much scale we want to track. If we have really long distances, we need to have more different frequencies. If we have a shorter period, we can probably do just a few of them. We have different options though, how we pick the frequencies. Because here we just divide the frequency to half when we're moving to like larger scale, but we can also use years, months, and weeks. Highest frequency will have, let's say, seconds. It's gonna be like this. Then we have minutes, which will be much slower. And technically, it's very hard to put in on the same scale. So we can put hours, then we can put weekdays, we can put days of the month, and it's like from 0 to 29, and we can have months from 0 to 11, and we have like a decade. So we normalize the values from, let's say, 2020 and 2030. So that will be like the full loop if we do change from 20 to 30. Why this approach might work better? If we feed this as input feature for our deep learning model, some of the events can be dependent on like days of the month or days of the week, maybe of the month itself, or the hour, like morning time, evening, and etc. So that one will very naturally fit into this system. And there is also one very interesting application of cycling encoding for time and dates that we can directly use them as inputs for transformer layer. Let me show you. So we have a transformer layer, and we have some input vector, but we need to element-wise calculate the sum of positional encoding with the input vector, where in NLP it's going to be work tokens, like word token 1, 2, 3, and etc. So positional encoding is very similar to what we just talked about, The only exception is instead of time, it uses position as input. So we have one frequency for lower order and so on. So we have positions first, second, third, fourth, etc. So we have points on the chart like this. This is our dense vector for first position. It's going to be x1, x2, x3. And then for 2, it's going to be x21, x22, x23. Those values over here, and etc. When we use data and time encoding, we can actually replace the position with exact time. So the difference that the events are not uniformly distributed, but really scaled how they appear in real life. So we have one event over here, and another one is very close to here, and the third one will be, let's say, here. And it can reflect the relative positions very accurately. We kind of can track more complicated trends. Yeah, this is one of the applications we can use for data time encoding with transformers, but we can also feed them just as an additional feature for each of the tokens. Let me know if you have any questions, how you like the video, send any feedback in comments.